Hello, welcome to you folks attending the CTE-inspired virtual conference hosted by ICEV. I'm Mark Zidon, and my presentation is called Building Your Toolbox, Teaching Resources for Engine Mechanics. I'm a professor at the University of Wisconsin-Platteville, where I teach agricultural mechanics and agricultural education courses. In my presentation, I will show you how you can use a computer program, such as PowerPoint, to illustrate what you teach, specifically in teaching about engines. I believe illustrations help students grasp concepts more readily. After more than 45 years of teaching, this past year has changed things up for me as well as many others and sent us back to being new teachers. Zoom and PowerPoint have been big players in education during the COVID pandemic. I've had some real misgivings about PowerPoint. I've seen too many times when teachers simply take the notes we once used on overhead transparencies many years ago and turn them into PowerPoint slides, perhaps with some bells and whistles. As a result, many students complain about PowerPoint fatigue. On the other hand, PowerPoint can be a powerful tool in illustrating how an engine works. So in spite of my frustration with PowerPoint, I have used it quite extensively in my teaching. Creating illustrations on PowerPoint is actually quite simple. Allow me to demonstrate. Here I have drawn a rectangle on a PowerPoint page. By using a gradient fill, I have made the sides of the rectangle darker and the center lighter. In doing so, the rectangle begins to look like a cylinder. This is the beginning of an engine piston. By drawing 3 horizontal lines across the rectangle, I now have 2 compression rings and an oil ring. A dark circle becomes the piston pin or wrist pin. I can now group these components together. With the components grouped, I now animate this with motion path lines. This moves my piston downward with a smooth start and a smooth end. Next, I will add auto reverse. These are all components on the animation panel of PowerPoint. Now that I have the piston going down and back up, I will go to Slideshow Setup and select Loop Continuously, and I have the piston going up and down until I hit Escape. With the single slide, along with a little creativity, and some options built into PowerPoint, I can illustrate to students how the piston moves in an engine. With the piston moving down and up, I add the words intake, compression, power, and exhaust. Finally, I add the intake and exhaust valves to illustrate how they move with the piston. I do know that you can find animations such as this on the internet. YouTube, I'm sure, has several such animations. However, with a little creativity, you can create your own, and you can control it to show the students what you'd like to have them see. Let's compare this to how we might typically teach. That is, we teach by giving notes, and the students write down these notes. So here we have notes on the 4-stroke cycle engine. The intake stroke, intake valve is open, exhaust valve is closed, piston is moving downward, and the air fuel mixture is being brought into the cylinder. Compression stroke, intake valve is closed, exhaust valve is closed, piston is moving upward, and the air fuel mixture is being compressed. Power stroke, intake valve is closed, exhaust valve is closed, piston is moving downward, and the air fuel mixture is burnt, pushing the piston downward. And finally, the exhaust stroke, intake valve is closed, exhaust valve is open, piston is moving upward, and the burnt gases are being expelled from the cylinder. So let's think about this. Will a student learn more by taking notes or by watching the engine in action and determining what is happening? I, for one, prefer to challenge the student's ability to think critically by analyzing and synthesizing. If we put students in pairs, have them watch the process of this engine working, and then tell us what is happening, I think they will understand the concept better and remember longer. As a second example, I will present an idea of how to teach the concept of magnetic induction that happens in an engine coil. Here's how I did that. In this example, I am going to make a coil for an engine. I begin by making a rectangular shape with rounded ends. I change the color to a copper color. I use gradient fill to make the ends a little darker and the center a little lighter. This is to give the shape a round appearance. Then I tilt the shape slightly. I duplicate the shape to make several coils, and I group these together. By adding small circles on the end of each shape, I create the appearance of a cross section. Now the students are looking at a cross section of a coil. Inside the coil, I add another coil using the same process, but this coil has smaller wire to represent the secondary winding. Inside that coil, I add an iron core. Around the coils and iron core, I draw a canister. And I make this canister a bit transparent. Now the students can look inside the engine coil and see that there are primary windings, secondary windings, and an iron core. I've always had difficulty teaching students how electricity can be created in a secondary winding from a primary winding without the two being connected. The student learner outcomes for this lesson are to describe the principle of magnetic induction and to apply magnetic induction to electricity in farm wiring or in automobile ignition systems. So, how does magnetic induction work? Here we have an engine coil. Inside the coil we have primary windings, secondary windings, and an iron core. The question remains, how does electricity get from the primary coil to the secondary coil? The answer is magnetic induction. But how does magnetic induction work? A few years ago, I stumbled across an idea involving copper tubing and magnets. So I got myself a piece of copper tubing and bought a cow magnet. I had half-inch copper tubing, a cow magnet, and a steel rod that I made to look like a cow magnet. When the steel rod is dropped, it falls as fast as gravity pulls it downward. The cow magnet, however, falls much slower. The falling magnet creates eddy currents. These are currents that swirl like an eddy in a river. In turn, the swirling eddy currents create a magnetic field. The magnetic field created by the eddy currents push back on the magnetic field of the cow magnet, and this slows the fall of the cow magnet. As long as the magnet is moving, it creates eddy currents. Let's look at that again, this time with the magnetic field created by the eddy currents. I've labeled the north and south pole of the magnet. When the magnet falls, the eddy currents create a magnetic field with the poles pushing against each other. In conclusion, electricity creates a magnetic field, and a moving magnetic field creates electricity. Allow me to put these ideas together in a short lesson presented on engine electrical ignition systems. I'm Mark Zidon, and this is a lesson on engine electrical ignition systems. This lesson will deal with what is known as the Kettering system. This system uses breaker points. Although breaker points have long since been replaced with a transistor system, the Kettering system is more easily explained. The same principles still apply with the transistor system. The problem of an ignition system is that the 12-volt battery needs to deliver 20,000 volts or more to the spark plug. The spark plug has an air gap that is 30 thousandths of an inch or more. Air is not a good conductor unless it is ionized. Very high voltage is required to create the spark. 12 volts won't do it. The electricity must be transformed to a higher voltage through a coil. The coil has primary windings and secondary windings. The primary windings are connected to the battery and to the engine ground. The battery is also connected to the engine ground, completing the circuit. The secondary windings are connected to the ground and to the spark plug wire. Because the spark plug is also connected to the ground, the circuit is also completed in the secondary windings. The primary windings have relatively heavy wire with a lot less windings compared to the secondary windings. The secondary windings have very fine wire with many, many more windings compared to the primary windings. At the center of the coil is an iron core. This iron core serves to enhance the magnetic field created in the primary windings. The parts of a coil are the output terminal where the spark plug wire is attached, two primary coil terminals, one going to the battery and the second going to the ground, the primary coil, the iron core, and the secondary coil. Notice the gauge of the wire and the number of windings in the primary coil and the secondary coil. The battery is connected to the primary windings. This builds a magnetic field around the primary windings. This magnetic field is used to induce electricity in the secondary windings. A moving magnetic field can induce electricity into a wire. It is necessary that the magnetic field move in order to induce the current into the secondary windings. The primary wires are wound to concentrate the magnetic field. The windings in the secondary coil are also wound to concentrate the induction of electricity. The question is how to make the magnetic field move. When the circuit begins, the magnetic field moves outward. The magnetic field collapses when the circuit stops. Breaker points are used to start and stop the current. These are the breaker points. When the breaker points close, the magnetic field builds outward. When the points open, the magnetic field collapses inwardly, passing through the secondary windings, and induces current in the secondary windings. Current is induced in the secondary windings, and this is known as magnetic induction. The voltage is increased because the secondary windings have many, many more windings than the primary windings. To review, points close, and the magnetic field builds outwardly. The points open, and the magnetic field collapses, and a spark is induced in the secondary windings. A condenser is added to prevent the points from wearing. The low voltage parts of the system include the battery, the breaker points, the primary windings, and the condenser. The high voltage parts include the secondary windings, the spark plug wire, and the spark plug. To summarize, points close, electromagnetic field builds in the primary coils, points open, the magnetic field collapses passing through the secondary coil, and a high voltage current is induced in the secondary windings. Problem is solved. 12 volts at the battery are changed to the needed 20,000 volts at the spark plug. The coil is a transformer that changes low voltages to high voltages. The breaker point system has been replaced with a system that operates with transistorized switches. I'm Mark Zidon, and this has been a lesson on electrical ignition systems. Before you call me out on the ignition system with breaker points, I understand that breaker points went out almost 50 years ago. It's just that breaker points illustrate the concept in an easy-to-understand fashion. That is, points closed, current begins. Points open, current stops. This is much easier than explaining how a transistor switch works. It's the starting and stopping of the current that is important to understand how the magnetic field builds out and collapses. For my final example, I have a portion of a lesson on carburetors. I'm Mark Zidon, and this is a lesson on how carburetors work. The objectives of this lesson are to identify the parts of a carburetor, to describe the function of each part, and to explain the function of airflow through the carburetor. Here we have a Briggs & Stratton 2-piece flow-jet carburetor. And this is the inside of that carburetor. The venturi is the heart of the carburetor. As air moves through the venturi, it is restricted and speeds up. This creates a low pressure area in the venturi. A nozzle is placed in the venturi. The whole of the nozzle is placed in the low pressure area. The low pressure is not enough to draw fuel a long distance up the nozzle. Therefore, the fuel level must be kept just below the hole in the nozzle. The float maintains that fuel level in the float chamber. A good comparison of this float is to look in the back of your bathroom toilet. You'll find a float that allows that tank to fill up, but stops the flow of water when it gets to the correct level. Watch what happens as the float chamber fills with fuel. When the fuel level is high enough, the float valve shuts off the flow of fuel. Air enters the carburetor on the intake stroke. When the piston moves from head dead center to crank dead center, it draws in air. This air comes in through the carburetor. Notice the air entering the carburetor. As the air passes through the venturi, it draws fuel to combine with the air. Notice the fuel being added to the air in the venturi. The main needle valve controls how rich the air-fuel mixture is. A lean mixture will have less fuel to air, whereas a rich mixture will have a higher fuel to air ratio. Let me draw your attention to both the main needle valve and the air-fuel mixture in the venturi. When the needle valve is open, the mixture will become richer. The throttle controls the amount of air-fuel mixture that goes. I'm sure you get the picture without seeing the remainder of that lesson. I feel the need to emphasize that good teaching begins with clear student-learner objectives. For example, these lessons contain objectives such as describing magnetic induction and applying it to the engine's ignition system, or explaining the importance of airflow through the carburetor. Along with clear objectives, good illustrations combined with good activities enhance student learning. There are many activities to demonstrate Bernoulli's principle and how this works in the venturi. For example, blowing air under a paper tent will demonstrate how the low pressure area is created. Finally, the carburetor lesson would not be complete without including the disassembly and reassembly of a carburetor. If all this seems like a lot of work, let me assure you that in fact it is. But you don't need to reinvent the wheel. There are a lot of good materials already developed to help you. This would be a good point for me to put in a plug for professionally developed, prepared materials like ICEV has to offer. This is a lesson on the assembly of small gas engines. Notice that early on objectives are listed. And the objectives are linked to standards and career pathways. Lesson plans give the teacher lesson-by-lesson directions. And finally, laboratory activities are outlined. To accompany this, a video augments the instruction. This video on assembling a small engine is professionally produced with clear narration and video. Kohler's senior trainer specialist Scott Mack narrates the process with clear pictures that takes the students through the process.
The goal is to provide a fundamental knowledge necessary to pursue a career in the engine service and maintenance industry. To prepare our engine for reassembly, Clean and inspect all parts according to the inspection and service procedures prior to beginning the reassembly process. Repair or replace damaged or...
As you can see, there is no babbling or frustrating PowerPoint note-taking, just clear teaching. As I bring my presentation to a close, let me summarize in this way. The most important thing is to have goals for your students. Good teaching begins with good student-learner objectives. Your purpose is more than just getting through the day or the lesson. Measurable objectives are a must. Good illustrations can help students learn mechanical principles. Hearing, seeing, and doing enhance the student's ability to learn and retain what they have learned. You can do it yourself. Homemade visuals work for students and also help you become more connected with what you are teaching. However, you don't need to reinvent the wheel. There are plenty of materials you can find. But do more than babble to lengthy notes. Include good demonstrations and good laboratory activities in your mechanics lessons. This is how students learn best. I'm Mark Zidon from the University of Wisconsin-Platteville. Thank you for watching my presentation on teaching resources for engine mechanics.